Lesson 1 of Chapter 3 is on exponential functions, and so we're going to discuss what an exponential function looks like, both algebraically and graphically. So to start off with, every exponential function is in the form f of x equals a times b to the x, and so when it's in this form, the a value represents the initial, and the b represents your base. Now your base is going to tell you whether it's growing or decaying, because we're going to have exponential growth and decay models. The initial value is going to tell you your y-intercept. So I got some non-examples right here. Those are all examples of exponential growth and decay models, and here are some non-examples. So if it's an exponential function, you have to have a number raised to a variable x. So with the growth and decay models, you can see the growth model on the left. Here's all the characteristics of it. The domain is all real numbers. The range is greater than 0. There's a y-intercept at 1, an x-intercept none at all, because it's never going to touch the x-axis. There's no minimums or maximums or no extreme values. And there's a horizontal asymptote right here at y equals 0. And so that's just the x-axis, and then you can see the end behavior down below. As you go really far to the left, it gets closer to 0. As you go really far to the right, it increases without bound. And this function is continuous. An exponential decay model looks pretty much the same, except for it's reflected about the y-axis. So the domain, again, is all real numbers. Range is greater than 0. Y-intercept at 1. No x-intercepts. No extreme values. No minimums or maximums. Horizontal asymptote, again, here at 0. And then as you go really far to the left, it increases without bound. As you go really far to the right, it gets closer to 0, and it's continuous. So one of the main things I want to talk to you about is deciding or determining if it's a growth or decay model. So to do that, you have to look at the b value. On this one, our b value is 3. Since b, in this case, is greater than 1, it's a growth model. Okay? The next one, it looks like the base value is 2, but 2 to the negative x is the same thing as 1/2 to the x. Thus, my base value is 1/2, and since 1/2 is less than 1, then it's a decay model. Next one, example 1a. The base value appears to be 6, but with the negative exponent, this is going to be a decay. 1b. Base value is 5, that's bigger than 1, so it's growth. 1c, the base value is 1/4, that's smaller than 1, therefore it is decay. Next, I got a bunch of exponential functions. Let's talk about if they're growth or decay. Number 1 would be a decay. Even though the base value appears to be 2, it's got a negative exponent, so the base value is actually 1/2. Number 2 would be a growth because the base value is 5. Number 3, the base value is 0.2, that's smaller than 1, so that's decay. Number 4, the base value is 6, that's greater than 1, so it's growth. Number 5, even though there's a negative sign in front, the base value is 0.25, and that's less than 1, so that's also decay. Number 6, the base value appears to be 1/10 or 0.1, but with that negative exponent, this is the same thing as 10 to the x. With the base value being greater than 1, this is growth. Number 7 has a base value of 1/6, therefore that is decay. Number 8 has a base value of 1/3, therefore that is also decay. Number 9 has a base value of 2, so that is growth. And number 10 has a base value of 1/5, and so that is decay. So hopefully you can tell by looking at the base value whether it's growth or decay. And from there, I want to talk about transformations. Now we've got our two rules. Anything inside affects the graph horizontally and illogically. Anything outside affects the graph vertically and logically. So if we compare 2 to the x to this function here, 2 to the x plus 1, obviously you can see there's a plus 1 in the exponent. And the inside part of an exponential function is going to be in the exponent. Therefore, the transformation is going to be to the left 1 unit. And so the graph on the right, the blue graph, is the original function 2 to the x. The red one is 2 to the x plus 1. So if you took the blue graph and moved it to the left one, you would have the red graph. Part B, we have 2 to the negative x. And so if we're comparing that to this function, the negative sign is inside. Therefore, it's a horizontal reflection about the y-axis. And so the blue graph you can see is 2 to the x, and then 2 to the negative x would be the red one, just a horizontal reflection. Next, we got two different transformations. If we compare it to 2 to the x, we've got a 3 that's being multiplied out in front. Since that's not on the inside, it's a vertical stretch of 3. The reason it's a stretch is because if you multiply by a value bigger than 1, it's going to get bigger. And this is on the outside, so we're thinking about that logically. The negative sign is also on the outside, therefore it's a vertical reflection. If you look at the graph on the right, the blue graph is just 2 to the x. If you stretch that vertically by a factor of 3 and then reflect it vertically about the x-axis, you'd get the red graph. So the next thing I want to talk to you about is the number e. There's a famous mathematician named Leonard Euler. This is how you write his name. It doesn't look like you pronounce it Euler, but it is. And he basically discovered that if you take this expression right here and you start putting numbers in for x, bigger and bigger numbers in for x, you're going to end up with a value that's really, really close to 2.718. And that's what the number e is equal to. Okay, it's named after Leonard Euler. So with that being said, the function e to the x is an exponential growth function because e is a number that's bigger than 1. Therefore, it's growth. So this is what the graph of e to the x looks like. And we're going to use that to talk and compare about transformations. If we compare e to the x to e to the 4x, you can see that that 4 is on the inside because it's in the exponent. So since it's on the inside, it's a horizontal. Now we have to think illogically. And if you multiply by 4 illogically, it's going to get smaller. So this is a horizontal shrink of the reciprocal of 4, 1/4. And if you take the blue graph and you horizontally shrink it by a factor of 1/4, you'd get the red. Next one, we're comparing e to the x to e to the negative x plus 3. So the negative sign is on the inside, so therefore that's a horizontal reflection. And then the plus 3 is on the outside, so that's a vertical shift up 3. And if you took the blue graph and you horizontally reflected it and moved it up 3, you'd get the red graph. Next, if we compare e to the x to 1/2 e to the x, that 1/2 is on the outside, therefore it's a vertical shrink of 1/2. If you took the blue graph, vertically shrunk it by a factor of 1/2, you'd get the red.